In the previous video, we argued that for new test points, or in other words, for the validation set, there is an optimal K that would produce the best performance, and that K is, well, it's somewhere between 1 and the size of the training set. So what happens when K is just equal to the size of the train set? Well, in that case, for any point that's a test point, and in fact any point that's a training point, all the training points are the neighbors, right? So everything is the neighbor for this guy, everything is the neighbor for this guy. That means that the performance, that the output is going to be always the same, which is, well, if there's more green points than there is pink points, then the output is always going to be green regardless of the input. So what does it mean? Well, it means that for the validation set, the performance when K is equal to the train set, well, it's just going to be the proportion of, in this case, green points, in general, the proportion of the majority element in the validation set, which should be the same as the proportion of the majority element in the training set, because of course, the idea is that the training set and the validation set come from the same source. They're the same kind of data. If that weren't the case, then there is no point in trying to use the validation set, right? So, okay, so that means that if we try to draw the curve of the correct classification rate versus the K, where the K is the K in KNN, well, that means that we'll eventually end up, somewhere that's, if we have two classes, larger than 50%, right? But it's going to be somewhere here. Where do we start? Well, we start at K equals 1, and we start somewhere. And what we argued is that, in general, in the generic case, the performance would go up until a certain point where it would be optimal. So the performance would go up until, let's say here. So the curve would look kind of like this, okay, where this is the best K. What about the training set? What would the curve look like for the training set? Well, when K is equal to 1, what happens? Well, when K is equal to 1, you're saying, well, what's the majority vote for the 1 nearest neighbors for this point? And the point is in the training set. Well, the answer is, well, it's always going to be green here, it's going to be pink here, right? Because each point is its own nearest neighbor, which means that for points in the training set, the 1 nearest neighbor using that same training set is always going to give the correct answer. So that means that we'll start out at 1, basically. Okay? Now, what's going to happen once you move to, let's say, 3 nearest neighbors? Well, you won't be doing as well, right? Because sometimes you'd be wrong, whereas here you would never be wrong. So that means that the performance for the train set is going to decrease a little bit as you increase K. And in fact, the more you increase K, the less it matters that you're talking about the training set and not the test set. The only advantage of running K nearest neighbors on the training set is that each point is its own nearest neighbor. But of course, if you're looking at like 50 nearest neighbors, the fact that one of you is yourself, well, it helps a little bit, but not by much. Which means that eventually the behavior on the training set is going to look very much like the behavior on the validation set, except slightly better. So that means that we'll decrease here and we'll start looking very much like the performance on the validation set, except a little bit better, and we're getting closer, and eventually we'll just converge to the same thing. So like that. Or maybe we'll be a little bit higher. But basically this is going to be the story where this is the training set and this is the validation set. So this is, of course, for the case where everything basically works. Sometimes things break. We'll talk about it in the next video.